thing, and then say, well, maybe it doesn't. What about d squared x dt squared? What if it's in there, right? And the answer was, let us add a variable, which is the velocity, which is dx dt, and then we get a system of equations for dx and v, right? And this one then is v, and this one is whatever that one was going to be. It was going to be f of x, right? So let us do that here. We have a dynamical system. We have a second derivative. And so we're going to write u dot equals v, and v dot equals d phi du minus cv. So that's equivalent to the equation that we wrote before. If c is equal to 0, this is a Hamiltonian system. That's going to be the subject of tomorrow afternoon's class. Isn't that right? Yeah. Let us write the Hamiltonian. The Hamiltonian, that's just another way of saying the energy. Remember that that was minus phi. That's going to be the same thing as this. So we'll write the Hamiltonian, minus phi plus 1/2 v squared. And we see that it's of this form. This is not a gradient system. You see that it's different because we have a minus sign here, and here we have a cross. We don't have u dot equals dh du and v dot equals dh dv. This is u dot equals dh dv, and v dot is minus dh du. So it's kind of the curl. This is Hamiltonian system. With the c not 0, it's not a Hamiltonian system. You cannot find an h such that this is the case. Okay, so this is how we're going to study it. Now let us look at a particular case for phi. Let us look at, for phi, we'll write, from minus d phi du, we're going to write mu u minus u cubed. Okay, I remind you, we're back here. We're going to write, instead of minus d phi du, we're going to write mu u minus u cubed. You'll recall that if we just wrote mu u minus u cubed, we would have pitchfork bifurcation. But now we have this other term here, this d squared dx squared term. And we're trying to figure out how to use this method for studying that. We have thus our pitchfork bifurcation and a diffusion term. And this thing here is called the Ginzburg-Landau equation. And we know what we would do. To find steady states, we would set this to 0, and we would have mu u minus u cubed plus d squared u dx squared equals 0. Now, to study it by this means, the means that we're going to talk about, we need to write this again in terms of the potential. So let us, okay, and before I said this about the gradient systems, I said way back here, I said we could just, if we were in 1D, we could just integrate, and so too here, we can just integrate, since we just have one variable. We find that mu u minus u cubed is minus d phi du, when phi is a fourth order function. Naturally, we're integrating a cubic function, so we get a fourth order, right? Okay. It's just integration. Everybody gets that. So the steady states satisfy this. Okay, and let me remind you, why am I doing steady states? Because for the moment, I'm talking about c being 0. So I'm not talking about traveling waves. There's none of this friction that was so weird. We're only talking about steady states. We're just going to talk about steady states of this equation in this new way, in this spatial analysis way. Okay, so here we are. Okay, so now let us look at it in this, okay, again, where we've turned space into time. We have this d squared u dx squared, and we're going to make that a dt squared, and thus that will turn it into two first order in time systems that are here. Okay. This is the same thing as this. This thing here is the steady state equation of the time dependent. We start off here with a pitchfork bifurcation to which we've added diffusion, and we seek steady states for this. Now we want to put this equation here, this equation, in the terms that that spatial analysis sort of form. So with this equation here, we're going to put it into that other form. That's easy because we're going to write this as minus d phi du here with this phi. And here we've done it. These are steady states, and this is what they satisfy. And that's equivalent to two first-order equations. Okay, so far I've done nothing. I've just manipulated. The only thing I did was to integrate a cubic to get a fourth-order equation. Okay, that's it. Otherwise, I did nothing. Now, I have this new dynamical system where I've written dots here so that you remember that it's time, but remember somewhere way back in your mind, forget it for the moment, but bring it back, that this time is really space, that came from the dx squared. It's not space right now. Right now it's time. Okay, we're going to analyze this system. When we analyze this system, we look for fixed points, u dot equals 0, v dot equals 0. We look for v equals 0 and d phi du equals 0, meaning we look for extrema of that quartic equation or zeros of the cubic equation, just as we've done many, many times. Right? And we find that v is 0, that's what it has to be for a fixed point, and u is 0 or plus or minus square root of mu. We've found this many times before under many different, starting from many different starting points. Right? Okay. So that's the same as if we hadn't put in diffusion. That is to say, if we had started off with just this, and I'd said, let's find the steady states, we would have said, oh, u equals 0 and u equals plus or minus square root of mu, without all this fancy stuff, without turning space into time, without diffusion, right? I would have said that. But now, for the first time, we're going to get something that's different. This is now, instead of being, our dynamical system is two 1D equations. We have a Jacobian. Since there is v dependence here in this top equation and no u dependence, the first row of our equation is 0, 1. Our Jacobian is 0, 1, right? No derivative with respect to u, but a derivative with respect to v. So 0, 1. Everybody agree with that? Now for the second row, I'm going to take the derivative of this with respect to u and with respect to v. When I take the derivative with respect to u, I'm going to get phi double prime. When I take the derivative with respect to v, well, there isn't any, 0. Phi is, of course, we remember what it is. Phi is the quartic equation. D phi d, the first derivative of phi is the cubic equation. If you take the second derivative of phi, which is what we have to do, we're going to get a 2u squared, but with what sign? We're going to get a 2u squared when we take, a mu minus 2u squared. So let us do that. We have, okay, our u bar is plus or minus square root of mu. So when we take 3u squared minus mu, that gives us 3 mu minus mu. That gives us, sorry, why do I have minus mu? Oh, yes, right. Okay, so two possibilities. U is 0, in which case you get minus mu, or u squared is mu, in which case you get 2 mu. Okay, so this one, this u equals 0 has this Jacobian, and this u equals 0, this u equals plus or minus square mu, and that Jacobian. So if we look for the eigenvalues, okay, we can start to presage what we're going to do with Hamiltonian mechanics. The trace is 0, and hence you can find that the eigenvalues occur in plus and minus pairs. The eigenvalues of a Hamiltonian system, since the trace is 0, the eigenvalues, and the trace is the sum of the eigenvalues, then for a Hamiltonian system, the sum of the eigenvalues is 0, and hence they occur in plus and minus pairs. Okay. So there's two possibilities. First let's do that. They're lambda and minus lambda. Their product is the determinant, and the determinant is going to be either mu or minus 2 mu. So we see that there. So the product minus lambda squared is going to be either the product is going to be either minus mu or 2 mu. That's what we said before, right? let's see, all right, let me just go through it. The product of the eigenvalues is either mu or minus 2 mu. If it's, and the product of the eigenvalues is minus the square of lambda, and either you get plus or minus square root of minus mu, in this case, or you get plus or minus square root of 2 mu for that case. There. So either, okay, recall that as before, we have these new states only for mu positive. So for mu negative, these eigenvalues will always be real. Am I right? For u equals 0, we will, and for mu negative, these will be a plus and minus pair. And in that case, we call that a saddle, a hyperbolic fixed point. The motion near there, near a saddle, looks like this. And the other possibility, when you have a Hamiltonian system meaning a trace of 0, is that it's a center. We did these as special cases. Okay? So those are the only two possibilities when the eigenvalues are plus and minus pairs. And we see that we only have these new solutions, plus or minus square root of mu, for mu positive. So these are always saddles. Whereas this center one here, the u equals 0, can be a saddle or can be a center. Okay, is that clear? These could be, for mu negative, they're saddles, and for mu positive, they're centers. These only exist for mu positive, and they are always saddles. Okay. So now let's draw pictures of this. That's here. Forget the picture above. This is the u-v plane. Those are our two variables, are u and v, right? U and v. And let us draw those fixed points in that 2D space. Here's u, here's v. We said that for mu negative, we only had one solution, which was all the steady states have to have v equals 0. So they're all along this line, for sure. For mu negative, you only have one, which is at 0. For mu positive, you have two of them. Excuse me, an old one and two new ones. You have the 0 and you have the plus and minus square root of mu. Right? So we go back to that. Plus and minus square root of mu for mu positive. But we still have u equals 0. We said something about being center and saddle, and that is what is drawn here. The trajectories near a saddle look like this. And we said that for mu negative, this center point was a saddle. That is to say, suppose, I haven't drawn the direction of the arrows, but let's draw them this way here. We go in here, and we come out here, or else we go in here, and we come out here. At mu equals 0, there's a pitchfork bifurcation, a Hamiltonian pitchfork bifurcation, and we end up with 3 fixed points, here, here, and here. The new ones are saddles, meaning that they have eigenvalues that are plus and minus some positive number here. The new ones are saddles, again with these cross trajectories. You either do this, and the center one has become, the one in the center has indeed become a center, meaning you just go around it. And I remind you, I keep saying Hamiltonian, there's no dissipation here as far as this system goes, and that is shown by the fact that you're on a circle, you just stay there. You put all volumes in phase space are preserved. Okay? You can't spiral in because that would violate that. Okay, so let's discuss the kind of trajectories you have and what they mean. What they mean is written here. You remember I told you that the potential was now going to be opposite. This is minus phi. You recall that phi, this is minus phi, which has a minus u to the 4th. And we need that as our potential. We wrote that here. minus phi is our potential so that we can go downhill, otherwise we're going uphill, and that would be weird. So minus phi is our potential, and phi, we recall, is because then minus phi is minus u fourth. So here it is, here's a minus u fourth like this. Okay, so what are these different trajectories? Supposing we start off with a high velocity and to the left. We're on the left and with a high velocity. So we're on the left and we have a high positive velocity. So we go, and that's coming down here. And we reach here, the center. We have some velocity as we're doing it. We're at u equals 0, but we don't have 0 velocity, and we keep going. This is it's at the top of the hill. You can imagine, since we're turning potential energy into kinetic energy to potential energy, it's at the top of the hill that our velocity is lowest. And indeed, that's the case. We come down on one of these trajectories, and our velocity is lowest, and we come back up. We have symmetric possibility. There's nothing saying left, right. We could be starting off from the right with leftwards velocity, so our u dot is negative, and we're on the right, and we do this, and we get to here, and that's where our velocity, our leftward velocity, negative velocity, would be closest to 0, and then we would turn around and go towards the left at an increasing velocity. Then we have another set of trajectories where we don't have enough velocity to make it across. See, we start off with a velocity that is here, and we go up, and we don't make it, and then we come back down. And that is here. We start off, say, here, and we never make it. We make it to this value, say up to -1. We make it here, and then we start going back down again. We have positive. Excuse me. No, I'm not doing it right. We must be starting from. We're starting from the left. So we're here, and we have velocity, which is positive. So we're starting here. Yes, so our directions like this. We start here. We go to the right. We don't make it, and we come back down to the left with negative velocity. And of course, we can do the opposite. We can do that. Okay, so that's this situation. We can draw it a third way, which is u as a function of time. We start off with back at infinity. We have some velocity, some positive velocity. This is one that's going to make it across. Some positive velocity. Then we have the velocity gets less and less, the slope gets less and less, but we're still at this, we cross with some slope. You see there's some slant here. We cross with some slope, and then we continue. And now we have positive velocity that's shown by the slope, and also we're going towards u equals infinity. So now you understand all these. And now let's understand this. I think you'll have no trouble with, now that we've got all these things in our mind. We have taken our finger, that's what we did with mu, and we pushed this down, and we changed our potential. And now we see that we have some of the same stories and a little bit of new story. We can still start off here from the left with on the u negative and with u dot positive, but not have enough velocity to make it, in which case we do this. We can do the same thing on the right. We can have enough velocity that we make it all the way across. And again, at this point here, we have a lower velocity because we're at the highest point. Here we have a higher velocity. So we go down here, we have a low velocity, we have a higher velocity, that's the u dot, and then a lower velocity, and we make it across. But now we have new kinds of trajectories, which are in here, where we're just going this. We're just doing this. Remember, there's no friction in this one. We get to come back to exactly the same height. And that is a circle here. That's what that center is here. We have a maximum u at which we make it, the initial condition here, say. We start here, say, at 0 velocity. We go here, we go to where we have 0 velocity. That's our maximum location in u. That's our maximum velocity. Excuse me, our 0 velocity, our maximum u. And we keep going. So this thing here is one of these. So we have those trajectories as well. And those are limited by this heteroclinic trajectory, where you start here at this top of the hill with 0 velocity. You stay here forever, and then you go down, and then you stay here forever. Oh, And that's what a heteroclinic orbit is. You stay here forever, and now you go here, and you stay here forever. And then after staying here forever, you go back here. And so there are several kinds of trajectories here that you could draw here. Just as here, we could have drawn more than just this. This was a single trajectory that we drew, one of these. We didn't draw one of these. And now, not drawing these, we can draw one of these, which is, I guess it's one of these. And here we can draw the other kinds, the other trajectories. The trajectories that look like this, they look like periodic solutions of u of t, or x, or depending on. And then there's this one, and that looks like this. It has two plateaus: the place where you're here, and the place where you're here. Here's a plateau, and here's a plateau, right close here. Okay, so this just summarizes everything that we said.
Oh,
And-
sorry to interrupt. There is a seminar that has to start now.
Okay, well,
Thank
good,
you.
because I think we're finished. Not quite, but pretty much, yes. Okay, good. So we're finished. And now you've seen how to solve this equation in terms of spatial analysis. We'll do the last little details next time. Okay, and I'll get the homework printed out.
And are we operating in here this
We're
afternoon?
here this afternoon.